All right, folks. Today we're going to talk about what happens if you challenge me, especially if you challenge me to do some coding. Don't ever challenge me when it comes to coding, okay? Joking aside, let me just give a quick little introduction who I am. My name is Pontus Rydin. Yeah, it's a weird name. I'm from Sweden. That's my excuse. I currently work as a chief evangelist / geek at Wavefront. I'm going to talk about what Wavefront is. A little bit about my background. I've been a developer for a lot of years before I did this. Done a ton of Java, done things like compiler design, all kinds of interesting things. Lately, I've really fallen in love with the Go language. I write a lot of code in Go. So there's going to be a little bit of talk about that. But specifically, we're going to talk about a challenge that I got a couple of months ago. Somebody came up to me and said, hey, you work for Wavefront. That's a cool platform. Here we go. There we go. So this was the question I got. Can you ingest and analyze 1 million events per second? 10 million events per second. I got the order of magnitude wrong there. Can you ingest 10 million events per second? And the answer was yes. Thank you. Any questions? No. Yeah. Now let's continue here. So what is Wavefront, first of all, right? So Wavefront is a metrics analytics platform that runs as a SaaS. It actually runs in AWS. It is known for its hyperscale. We currently have customers ingesting 4 million data points per second. Not saying that we can't do more than that. That's just the highest we've ever tested. It is, a multi-technology, cross-platform, cross-stack analytics platform. We do anything from metrics and histograms all the way down to traces. It's a very complete observability platform. I'm going to show you what it looks like at the end of this. But let's talk about the challenge I got, right? So here was the challenge. Can you take 10 million log records, a stream of that has some kind of syntax like that? It's basically comma separated or pipe separated, whatever it was, and then there was a URL encoded huge blob of things, about a kilobyte of stuff, right? Can you take that, break it down into metrics, and analyze that? Really analyze the crap out of that statistically. All right, so they wanted me to extract the naming, all the different dimensions of it, so there were different names of functions being called, different pools, different co-locations, different hosts, what have you, all kinds of things, and then pull things out of these arbitrary URL encoded fields. Once it was in the product, they wanted to be able to slice and dice that on any dimension, do any kind of statistical analysis on percentiles and what have you, right? And also, they needed that to be less than 10-second response time for any query. Actually, we ended up being like 1 second, but we'll get to that. So how do you do that with 10 million log records per second? And also, they wanted to do some tracing, right? So they wanted to collect traces, but they realized they can't collect 10 million traces per second and store them. So how do you do something like that? Well, you can do it brute force, right? You can take 10 million records per second, and you could just extract all those metrics and just shove it into Wavefront. As I said, we have handled 4 million records per second, so we probably would be okay with it. It would probably work, but it'd be really expensive because we charge per ingestion rate, right? So it was also probably be pretty slow when you're bringing up these queries. So, yeah, it would probably work, but not ideal. The other thing is that we can take, say, a minute average, right? Say, hey, let's average all these metrics that we're collecting once every minute and just send that in, and we reduce the data a lot. Awesome, great, yeah? Problem with that is that it doesn't really work because it gets boring and bland. You don't see the outliers. You can't do any statistical analysis. All the interesting events are actually hidden and just smeared out in an average. So it's not really that great of an idea, right? So more ideas. Can we just pick out the min and max for all those metrics, 10 million metrics per second. No, because min and max are really bad because one single outlier will destroy everything. I guess we could calculate a P99 and a P95 and P75. The problem was that this customer, they wanted it to be like P anything. So they wanted to do P45 and a half or something like that, right? So they really wanted to be able to tease out any kind of statistical information out of that. All right, so what you could do is just like equal-sized histograms. So basically, you take the data, you slice it up into buckets, say 0 to 10 milliseconds, 10 to 20 milliseconds, and so on and so forth, right? And you just put it in there. Problem with that is that you get really, really horrible resolution towards the outliers of the bell curve, right? And the outliers of the bell curve is typically what people are interested in. So, no, that didn't work at all either. And it gets really expensive if you want to have high accuracy. So, what we did in this case, we resorted to a data structure called T-digest, and here it's going to get really nerdy. There's even going to be some calculus, so beware, guys. So T-digest is a really smart data structure that somebody came up with just a few years ago. And it's for representing statistical distributions. So the idea here is that you have high precision where it matters, which is at the ends of the bell curve, right? So as you can see here, at the beginning of that bell curve, we can't really see it that clearly in this graph, but at the extreme ends of the bell curve, you have very, very, very tight, small buckets. And then the buckets get kind of bigger towards the middle, and then they get really tiny at the other end, right? The other thing about these is that they're super easy to merge. You can take two of these T-digests and put them on top of each other. And why is that important? Well, when you're doing things at hyperscale, what do you want to do? You want to do map reduce. You want to calculate things at a lot of different nodes and then reduce them in another node and then finally get it into your database, whatever. This is extremely map reduce friendly. Perfect for massive scale. And it turns out when you're doing percentiles, you're actually getting a 99.98% accuracy across the entire range. It's really an awesome data structure. Let's get super geeky here, right? So how do you do that? Well, you make a bunch of buckets. Each bucket has the mean value of that bucket plus the number of items in the bucket. All right? That's not that crazy. But they are non-uniform in size, right? Okay? Yeah. So this is how the bucket size kind of grows across the distribution. And it turns out that that's actually a really good function to use to calculate how the bucket size should grow. If you take the derivative of that, yes, I used Wolfram Alpha to do that. I didn't do that by hand. I probably could have, but I don't remember that much. What you're going to see here is that this is the size of each bucket, right? Towards the end, there are extremely small, tiny, tiny buckets. And what do you have towards the end? Very few values. So that's why you want those tiny buckets. Whatever values you have end up with very, very tight precision. And then towards the middle, you can have big buckets because it doesn't really matter. So that's not what your interesting data is anyway. So that turns out to be an absolutely awesome data structure for doing this. Cool. Now, when you want to calculate a quantile, like a percentile, all you got to do is basically use that mapping function and say, okay, I want to use the mapping function, you find the bin, and then you basically find two adjacent bins, and you can use some interpolation function between them. You can use like super fancy polynomial interpolation functions, but actually don't need to, because since they're so tight towards the end, it gets really, really accurate, even if you do linear interpolation. As I said, merge is extremely fast. I'm not going to go into why it's fast, but it's extremely fast to merge two of these data structures into one. Cool. And again, very good for MapReduce. So T-digest sounds great, right? But there was a lot of math and a lot of geekiness and a lot of stuff there, right? Well, luckily enough, of course, there are really good implementations. There's one for Java, which was the original one. There's a JavaScript, and there's a Go one. And of course, Wavefront, which is what I'm representing, we handle that natively. We actually use T-digest internally. So you can just send data to us, and we will build those T-digests for you. but we'll see.
These other examples, I can do T-digest by just using those examples on my data set.
Yes, yes, and we'll get to how that was done, right? All right, so here's the implementation. Here were the requirements. 10 million records per second. Each record was about a kilobyte in size. They have 50,000 distinct time series, so there's 50,000 combinations of the keys that make up a time series. I was given 50 nodes with 8 cores in each, and said, here's a cluster, you can have fun with it, play around with it. That works out to 20,000 messages per thread per second, right? Which works out to 40 microseconds per message. So I had 40 microseconds to read a kilobyte of data, to parse a kilobyte of data, to do a bunch of hashing and stuff on the kilobyte of data, and to do all these calculations and then send them out again. And I said, man, this is cool. I was like up for days and nights doing this. So in essence, it actually works out to about 30 microseconds plus some overhead, because there's a bunch of overhead and threading and what have you, context switching. Can we do it? Yes, we can. So this was my first implementation. So Wavefront is a cloud service, right? Sits in AWS, and it has proxies. So what you do is you typically deploy one of those proxies on site, or multiple proxies on site, and they're smart. You can send data to them and say, hey, I want you to T-digest this data for me. And they will do that. And they will create their own little T-digest, and then when you send them to Wavefront, they get reduced into one single one. So basically I had event sources, an event cruncher, which was basically the parser, and then each event I transformed into a metric, sent it to the proxy, and the proxy did all the calculation, and life was good. Problem is, this data transfer was extremely expensive, right? Because I'm sending, millions and millions of data points per second to the proxies, and the proxies were they could handle it, but I had to have really, really beefy proxies. All right, so the next thing I did was, there is a Go, because I used Go for this, we'll get to that. There is a Go implementation of T-digest. So I actually did all the T-digest calculations on these event crunchers, which meant that every minute I just had to send my histograms over here to the proxies. So there was one map here and the reduce, and then this one did further reduce and further reduce. So they kind of merged into a single histogram. That worked great until these things started to be very uneven in the data rates. So some of them went nuts and basically killed those event crunchers. Some did nothing, right? What do? You do that. You load balance it, right? So we load balanced any to any here, and then any to any to the Wavefront proxies. And I was really, really nervous about this because I was going to end up with so many partial histograms. So I don't know, I was nervous about it. And it turns out, and I did not invent T-digest, somebody else did, but I love it. It turned out that T-digest is so darn perfect for that, right? Because it is so merge friendly. So I ended up merging a little bit here, this little map and reduce, that in another reduce, and then final reduce, all kind of random data, but it worked perfectly, and it was super fast, incredibly fast. Okay, so that's how we ended up doing that. So, what were the challenges in building something like this, right? And I hope this is all. Yes.
On the last slide on the T-digest.
Yeah.
I just think, does T-digest work? Even though these are different data sets, you're doing individual T-digests on each one of those.
So they could be the individual data sets or the same data set spread out across all the nodes. It doesn't matter because T-digest is so easy to merge. It was designed to be MapReduce friendly. Okay, now design challenges: 30 microseconds to parse, categorize, filter logs, pull all those metrics out, and calculating the T-digest. Obviously, this was extremely CPU bound. It is basically only CPU and a little bit of networking. They had no storage whatsoever. So I picked the language for the event crunchers. I picked Go, because I love Go. And it is heavy, this was heavy on concurrency. And despite what you might have heard about Go, that it's not real threading and things like that, that was true for like Go 1.5. Go 1.12, I think I used. That is all fixed now, so you can really use massively parallel computers. It's faster than Java, and I was thinking of writing it C, C++, because there was no way Java was going to be fast enough to do this, right? So, but it's hard to maintain C, and honestly, my C is really rusty too, so yeah, there's that. And you have these easily distributable binaries, which matters when you're going to deploy this to 50 nodes. The other problem I faced was that the ID for a metric was made up of maybe 10 different values, right? So I had to store all those histograms in memory based on 10 different values. I tried different kinds of hashing algorithms. MD5 ended up being way too slow, which is not surprising because MD5 is not supposed to be fast. It's a cryptographic cryptographic hash that's supposed to be hard to crack. So it's not that fast. So if you ever have looked at murmur hash, or if you haven't looked at murmur hash, do so. It's a great hashing algorithm that is just incredibly fast. Murmur stands for multiply and rotate, because that's all it does. Multiply and then rotate the bits. So I calculated a 128-bit cache, and that's probably overkill, but that was fast enough to keep this list of all those histograms in memory. The other problem was, how do I max out 8 cores? Turned out that's not so easy to max out 8 cores. If you have a heavily multi-threaded application with threads communicating with each other and stopping each other and all these concurrency control, it is super hard to max out 8 processors. Protection of data structures is obviously an issue when you do things like that. And the first version was horrible. It suffered from tons of lock contention. So again, if you guys are developing in Go, I strongly urge you, use the RW, the read-write lock, which is a lock that allows you to have multiple readers and one writer, instead of just always locking it. That just tripled or quadrupled the speed or the throughput of this, just by saying that, hey, when I don't really need exclusive write access to this, I don't need to take it. So, great piece of advice, use them as often as you can. And I also had to create a custom hash table that was using read-write locks, because otherwise it was too slow. Cool. Parsing must take less than 5 microseconds. I tried regex-based parsing first. How do you think that went? It was more like 5 milliseconds, right? So I had to do a hard-coded state machine parser that was super hard-coded, right? And it had to be allocation-less, because you can't go on and allocating new strings all the time. You're going to kill the garbage collector. Turns out that Go's slice implementation is really, really good for that, because all you get is pointers into a big data structure. It never copies anything, right? Yeah, the arbitrary node handling each event we talked about. Merging histograms, well, T-Digest came to the rescue, right? And the client side of calculation of T-Digest, there's a great, that's the SDK I used. There's a bunch of articles there as well. Okay. So did it work? Well, kind of. The problem was that the event stream I got ended up being 8 million records per second and not 10 million records per second. It actually couldn't push through that much. But hey, what are you going to do? So here are all my different nodes. This is obviously Wavefront graphing this. And you see I peaked at 8 million. And it was running just fine. This is the P95 of how long it took. So this is not the average. It's the worst case how long it took to parse things, right? So it took about 9 microseconds to parse, which was 4 microseconds longer than I wanted. But I did the rest of the processing in 20 microseconds. I was pretty proud of myself, I got to be honest. That was fun. The load balancer, or the lack of load balancer stickiness, was not as big of a problem as I thought it was. I thought I would be killed because I had all these really fragmented histograms. It works. Turns out that T-Digest is super, super friendly for merging things. surprisingly low memory footprint. It was about a gigabyte per node. And keep in mind that I had to keep all these 50,000 histograms in memory. I had to have a buffer of at least 20,000 incoming messages to kind of smoothen things out. And it scales almost like 100% linearly to the number of nodes, which I thought was pretty cool. So, what was the net of this? Well, I got 10 million events per second. I was able to scale that down to 10,000 histograms per second. So that was a reduction factor of, because it turns out the log message and the histogram record is almost as big. So it's 1,000 to 1 data reduction, and they still could retain all their statistical information, which I thought was pretty cool. This was how many histograms I got in. So yeah, it's hovering around like 9, 10 million per second. So the stuff you can do, right? Well, I could do things like, hey, I could say I want something that is broken down per node, per function, per something, whatever, and I want the 95th percentile, or I want the 92.3rd percentile, or whatever it might be. It could do that because, as we said, it is so accurate towards the ends of the bell curve. Other things I could do was I could say, okay, all those histograms I had in the previous page. Oh wow, I thought I would go short. All those histograms I had in the previous page, I want to merge them. So I want to have a correct, because you can't average histograms, it's going to kill you. But the merge, since the merging is so fast in T-Digest, this took like less than a second to just do. This is probably, I don't know how many data points, but it's thousands, right? It took less than a second to do the merge. Really cool. And I can do things like this, red metrics. You know what red metrics is? Rate, errors, and duration, right? Now I could do this with any given percentile, so that was really cool. And I could do things like the P 99.99 or 99.92 or whatever I wanted. Again, it has 99.98% accuracy across the entire bell curve, so that was also super cool. And I also did, just because I could, I also said, okay, every once in a while, every X number of samples, I'm actually going to save an entire trace. Because it turned out these logs, the transactions were bound together with IDs, so I could reconstruct a full trace of it. So the way we did with that was we wrote a smart sampler, right? So we took emphasis, whenever there's an error, we sample more. Whenever something is close to the ends of the bell curve, we sample more, kind of the same idea there, right? And we captured a significant number of traces without losing relevance. What did we learn? Yeah, it's possible to do 10 million data points with Wavefront. We learned that simplistic aggregation is of limited use, and we learned that equal-sized histograms for collecting this type of data is useless. You need something like a T-Digest. And next step, I actually want to take this histogram or the log converter, and I want to make it generic so you can have some kind of description language. Probably going to compile that to machine code because it wouldn't be fast enough to just parse it in runtime. And I want to do this to pull a massive amount of logs from, say, Elasticsearch and push it into Wavefront. Oh, by the way, instead of being up partying last night, that's what I did. That's how geeky I am. So yeah, I actually ended up writing that. I don't know, probably out of time, but we can do. So this is what it looks like, right? So this is some data here. I can switch between different percentiles, and if I wanted the 95th or the 50th or the 25th, keep in mind these are 10 million data points per second. That is now reduced to just as valid statistics, and it loads in milliseconds. Let's see, probably over time here. Yeah. Yeah, actually, we're over time here, so the last slide was just a summary slide anyway. If you have questions, we got to be respectful to the next speakers coming up here. I will be like floating around here. I hope you found this extremely geeky and somewhat interesting, and just like a peek into a day in the life of what I'm doing and what kind of challenges people throw at me. My role is technology evangelist, but I'm really like an uber geek, and I write tons of code, and I have a lot of fun. I'm on Twitter, at P. Rydin on Twitter.
Can you repeat that?
There you go, at P. Rydin. There you go. And here I said I was going to go under. Yeah. Thank you, guys. Thanks for stopping by. And